Okay, so we still had to finish up just the end of chapter 3, and then we'll be quickly covering chapter 4. So basically, the left board is finishing chapter 3, the right board is all of chapter 4.
That's cool.
So chapter 4 should be an easier one. From chapter 3, believe it or not, we only had one more theorem to prove. But he's a big boy. So let's recap chapter 3 so far. Remember, chapter 3, we're now getting into geometry proper. And so I start to introduce you to the 4 basic components of any axiomatic system. What are the 4 things every axiomatic system has?
Undefined terms.
Undefined terms. What do we use undefined terms for?
Defining other things.
Constructing definitions. So you have undefined terms and definitions. What else?
Your postulates.
Your postulates.
Your axioms.
And then finally your theorems. The implications of your postulates. So you have your undefined terms, your starting words, and then your definitions, all your new defined words. You have your postulates, your starting assumptions, your starting things you assume to be true, and then your theorems, everything else that must be true if your postulates are true. That's it. So we started introducing, first off, our undefined terms. What were our undefined terms so far?
Point, line, plane, in between.
Point, line, plane, between. Those are our only undefined terms so far. And then let's quickly recap each of our postulates, make sure they all make sense. So remember that the author chose to split the postulates into groups. Completely arbitrary, just a nice way of grouping the postulates and referencing them. That's all. That's the only reason he chose to do that for. Okay, so our very first postulate is that every plane contains at least 3 points. Non-collinear points, so not all 3 of those points lie on a single line. You can't draw one line through all 3 of those points. Make sense? That's postulate 1-1. Postulate 1-2. What does that say? It says given any 2 points, there's one and only one line that goes through those 2 points. So postulate 2, there's exactly one line through any 2 points. Something like that. Make sense?
Yep.
3, every line has at least 2 points. Right?
Yeah.
Okay. So that was our first postulate group. And then, so those are our first 3 postulates, and then we had a group of 5 after that. So our next group of 5 is the one that gives us our postulates for betweenness. Remember that even though our undefined terms are undefined, that doesn't mean they're meaningless. The axioms, the postulates, the axioms, are what give your undefined terms meaning. The axioms tell us how these things behave. That whatever plane and point are, there's at least 3 points inside that plane. And whatever line and point and plane are, those 3 points aren't all on one line, whatever those words mean. You could replace these 4 words with complete nonsense words, and the geometry would still follow exactly the same. So here's the 5 postulates that tell us how betweenness behaves. And it behaves intuitively for how we use the word between, which is why we choose that word. So remember when you see A, B, C like this, what does this mean?
B is between A and C.
B is between A and C, perfect. So if B is between A and C, then A, B, and C are 3 points all in the same line. That's our first one. Next one. If A, B, and C are collinear, they're all on the same line, then it must be the case that either B is between A and C is between A and B, or A is between B and C. You have one and only one of those guaranteed. Make sense?
Yeah.
Next one, if you have 4 points on a line, then you can relabel them A1, A2, A3, A4, so that all your betweenness relations are A2 is between A1 and A3, A2 is between A1 and A4, A3 is between A1 and A4, A3 is between A2 and A4. So if you have 4 points on a line, you can always relabel them A1, A2, A3, A4, so that those are the only 4 betweenness relations. Make sense? This isn't how it was written in your book. I'm just scribbling something down to quickly explain it to you. 4. 4 said if you have 2 points on a line, then there's always a point between those 2 points. So if you have A and B, then there's always a D between A and B. Furthermore, there's always a point beyond your 2 points. So if you have A and B, there's a point C beyond the points. This is often called your line builder postulate. This is the one that guarantees us now that there's an infinite number of points on a line. Because if I have 2 points on a line, I'm guaranteed there's a point between them. Okay, I have 2 points on a line, I'm guaranteed there's a point between them. I have 2 points on a line, I'm guaranteed there's a point between them. And I can do that indefinitely. Make sense?
Yes.
And also going beyond. I can always find another point beyond, another point beyond, another point beyond. Some students like to think that this gives you, oh, so lines are infinitely long then. If I can always find a point beyond, does that mean my line goes on forever?
It was you, so.
If I can always go to a further point, if I always move forward some distance,
No, it doesn't.
am I guaranteed to move an infinite distance?
No.
If for all of time, I keep moving forward some distance. If I move forward some distance an infinite number of times, am I guaranteed to move an infinite distance?
No.
Of course I am.
Yeah.
Because it doesn't matter how small the distance I'm moving, do it an infinite number of times, it's still an infinite distance, right? Wrong.
Yeah.
Very unintuitively wrong.
What?
Don't worry, we'll make it make sense. So, I am going to move an infinite number of times, and I'm never even going to get to the end of the chalkboard. How do I do this? My first movement is to move half the way to the end of the chalkboard. My second movement is to move half of the remaining distance. My third movement is to move half of the remaining distance. My fourth movement, move half of the remaining distance. My fifth movement, move half of the remaining distance. If I do that an infinite number of times, where do I end up?
Very
Pretty much just at the end of the chalkboard. I didn't go an infinite distance. So you can go through an infinite number of movements and not cover an infinite distance. So this postulate only guarantees us that there's a point beyond our point. It does not guarantee us that we go infinitely far. Does that make sense?
Yeah.
Because that point could just be half the distance between me and the end of the segment, or some other place. Make sense? So, this does not give us infinite distance. This gives us infinitely many points on the line. And it's very hard to get intuition for how those aren't the same thing. But they're not. Okay. And then finally, our last postulate is a postulate that says a line splits the plane in two. If I got the plane and I run a line through it, it splits the plane into two sides. How do I know if 2 points are on the same side of the plane?
If that when you create a line segment through it doesn't intersect your line.
Right. So 2 points are on the same, here's L1. 2 points are on the same side of L1 if their segment doesn't intersect L1. And 2 points are on opposite sides of L1 if their segment does intersect L1. Good? Okay, so that was quickly recapping all the postulates we've talked about so far. And a couple of the definitions we created along the way. Definition of segment, definition of the side of a line. Let's remind you of one of our more important and more confusing definitions. This was definition 310. It was the interior of an angle. Do we remember the definition of the interior of an angle?
X is in the interior of angle O.
We'll say P.
P.
It's more standard.
Okay.
So P is a point in the interior of angle O. There it is. What do I know about that point if it's in the interior?
It's on the same side of L2 as R1 and the same side of L1 as R2.
And it's not on the race.
And it's not.
And-
Perfect.
no.
It's not on either of the rays, which means it has to be on one of the sides of the lines. Remember, if you're on one of the rays, then you're on one of the lines, and so you're not on a side of the line.
Right.
So just making sure you understand how the way he said actually covered that case. So yes, the interior point, if I know P's in the interior, I know it's on the same side of L2 as R1. So here's L2. What side of L2 is R1 on? That side. And it's on the same side of L1 as R2. Here's L1. What side is R2 on? That side. So you take this side of this line and this side of this line. Their intersection is the interior. Make sense?
Yeah.
Because our next proof is going to be about the interior. Jump ahead, just so you can see what our big proof is going to be. We're going to prove that if P is in the interior of some angle O, and Q is in the exterior of the angle, then the segment PQ intersects the angle.
We didn't prove that last time.
Now, I'll remind you of some of the things we did prove last time. So, the last two things we proved last time, Theorem 3.4 and Theorem 3.5, what was Theorem 3.4? We proved that if P and Q lie in the interior of an angle, then so does their entire segment. You remember that? Roughly, how did that go? We said, let's take a point on their segment and pretend it's outside of it. So let's pretend A is between P and Q, and it's somehow outside the angle. Then we said this segment then, APQ, is going to intersect this twice.
Which goes against the first
Theorem.
Which goes against the first theorem.
Yeah.
So we got this problem with intersecting lines too many times. And yes, good call back to Theorem 3.1. Theorem 3.1 was that two lines can intersect at most one point.
Yeah.
It's impossible to have a line intersect at 2 points. Okay, so, yeah. If P and Q are in the interior, so is the entire segment. And then Theorem 3.5, what did we prove? We showed that if angle O has sides, R1 and R2, we just need to label them. R1 and R2, there's angle O. And R is a ray from O, R is a ray from the point O, where R is not the same thing as R1 and R is not the same thing as R2. Then R lies entirely in the interior or the exterior of angle O, ignoring the point O itself.
Right.
So if you draw some other ray from O, and you don't draw R1 and you don't draw R2, then the ray you draw, if we were to draw this ray R, it would be entirely in the interior of the angle, and if we were to draw this ray R, it would be entirely in the exterior.
And it couldn't be on the line because it doesn't equal R1 or R2. Yeah.
It could be on the line, just pointing the opposite way. And that was one of the special cases we handled.
Oh, okay.
So we said if it's exactly opposite R1, then obviously it's not in the interior of the angle because it's on the opposite side as R1. And remember, what's the interior of the angle? It's all the points on the same side of this line as R1 and this line is R2. So that was a special case there. And we said then R, if it's not exactly on one of the lines, then R has to be on one of the sides of the lines. By definition of array. Array is, how do you get array? Pick any line, pick a point on the line. Now pick any other line through this point you want, and take all the points on one side of that line, and that gives you an array. And so, since these two lines go through O, which is where ray R starts, then the entire ray R is completely on one side of this line and completely on one side of this line. If it happens to be on the same side of this line and this line, if it happens to be on the same side of this line as R1 and this line as R2, then it's in the interior. And if it's not on the same side of this line as R2 and this side as R1, then it's in the exterior. So that's recapping. Now let's jump into the big theorem. Let me move my camera. Any questions about that quick review of what we did last time before I move the camera? So hopefully that re-primes you for what we're about to do. And I think that shows the whole thing. Okay. Thanks. Okay, so now, remind you what we're trying to prove. We're trying to show that if P is in the interior of angle O, and Q is in the exterior of angle O, then the segment PQ must intersect the angle O somewhere. Make sense? Okay, so we're going to handle 3 different cases. So here's our picture. Here's our point O. Here's our angle that we're talking about with rays R1 and R2. We're going to label them this way. L1 and L2 being the lines that those rays are on. And there's 3 possible places that Q could show up. So I know that Q is in the exterior of the angle, right?
Yeah.
So it could either be the case that Q is on the same side of P as one of the lines, but the opposite side of one of the lines. It could be that Q is on the opposite side of both lines, or it could be that Q happened to land on one of the lines. So these are 3 possible cases for Q. You might think, what about if Q lands on this line? Well, call this line line 2 and call this line line 1, and now it's the exact same as if Q landed there.
Right.
And you might think, what if Q landed over here? Again, relabel this one L1, this one L2, with R1 and R2, and now you get the exact same picture we have there. So relabeling takes care of those 2 cases, so we don't really have to worry about it. So it's really just these three cases we need to handle, and we need to show that in each of these three cases, the segment PQ intersects the angle. If it intersects the angle, what does that mean? It means it intersects this ray or it intersects this ray.
Or O.
O is part of both rays.
Right. Oh.
Make sense? Good. So that's what our argument is going to be over and over again, is establishing that PQ intersects one of the rays. And I've drawn out the subscripts in the order that we're going to handle them. Q1 will be the first case we handle, Q2 the second case, Q3 the third case. So case 1. Well, let's set up our picture. Let R1 and R2 be the sides of angle O on L1 and L2 respectively. Good so far? Just setting up our picture over there. Let P be in the interior of angle O. So P is just some point in the interior. That's all we know about it. And let Q be in the exterior of angle O. Q somewhere in the exterior. So just setting up our picture. Good? There are three cases that we need to handle. First case, Q is on the same side of one of the lines as P. In our picture, this is represented by Q1. Our second case is Q lies on one of the lines. That's represented by Q2. And then our third case is, or Q lies on the opposite side of both lines as P, represented by Q3. Good? Okay, so our first case. If Q lies on the same side of one of the lines as P, which line does it lie on the same side as? We're just going to call that line L2.
Yeah.
So if Q lies on the same side of one of the lines as P, call that line L2, call it L2. Then P and Q must lie on opposite sides of L1. So looking at this picture. So here we have Q. We're saying this is the case of our Q. We're looking at this point right now. P and Q lie on the same side of this line. Then they must still lie on opposite sides of this line right here. Right? And if P and Q lie on opposite sides of this line, what do we know?
There's an intersection between them.
That there has to be a point on the line between them. So if you were to create their segment, there would have to be some point here between them. What should we call the point? I think I called it R.
That's what it means for.
That's what it means for 2 points to be on opposite sides of a line. There's a point on the line between them.
Yeah.
Now, what remains to show is that R lies on R1. How do I know that the point between them isn't down here somewhere?
Because they're on the same side of R2. Because they're on the R1 side of R2.
Because they're on the R1 side of L1.
He's saying the R1 side of L2. So they can't be beneath L2 because.
Oh, that's what you're saying. So how do I know that this point can't be down here? Why can't R be right here? How do I know that my picture doesn't come down like that and then back up here, and the intersection of the angle is really over here somewhere? You've almost got it. So R is the point between them. What do I know about point R?
It's on one of the lines. You know that. It's on R1.
So R is on the segment PQ.
Yeah.
We know that. How can I argue that R lies on ray R1 and isn't down here?
Because it's intersecting the angle.
Well, we're trying to say it's intersecting the angle.
Well, I thought that was.
So all we know so far is that R is a point on this line between P and Q. I'm trying to say that R lies on the angle. I'm trying to say R lies on R1. I know R has to lie on R1.
Right.
How do I know that R can't lie down here? How do I know that my segment coming down over here then back up is an impossible picture? What would happen if Q came down to R and then back up to P?
It would intersect L2 twice.
It would intersect L2 twice.
Oh.
Now, we've already done this. You could prove it that way and you'd be redoing some work. But we already know if P and Q, we don't even need to say that. But we can just say R has to be on the same side of the line, has to be on the same side of L2 as P and Q. The reason I know that is P and Q are on the same side of the line. And so there's no point between them. That's not on that side of the line. What does it mean for 2 points, P and Q, to be on the same side of L2?
Their segment is entirely on.
That their segment is entirely on that side. That's what it means for 2 points to be on the same side. Now, you could have done it the way that you were thinking. Said, no, what happens if a point's over here? Well, then you get this double intersection.
Yeah.
And that works, but you're overthinking it.
You already proved it.
You're already done. If P and Q are on the same side of the line, their whole segment has to be on the same side of the line.
Which means it has to intersect R1.
So that means R is on that side of the line.
Yes.
And all the points on L1 on that side of the line is R1.
Right.
Okay, so I think you got big picture. Now I'm just going to say it in words. So if Q lies on the same side of one of the lines as P, call that line L2, then P and Q must lie on opposite sides of L1. P and Q must be on opposite sides of L1. So then, get used to this notation. There exists R, the point R, there exists R in L1. Dense to read, gotta get comfortable reading it. So then, there exists R in L1 such that R is between P and Q. Right?
Yep.
So there has to exist a point R on the line L1 between P and Q. And since all of segment PQ lies on the same side of L2, then R must be in R1. It can't be down here, because that's not on the same side of L2 as P and Q. And so PQ intersects angle up. Since it intersects this right, it intersects angle up. That's our first case. Think you got it? All right, let's move on to our second case, case 2. Next, if Q lies on one of the lines, which line does it lie on? We'll just call whichever line it lies on L2. Relabel your picture. So if Q lies on one of the lines, say L2, then P and Q must be on opposite sides of L1. Let's see how we're going to get a problem with this picture. So we've already handled the case Q1. Let's just get that out here, clean up our picture a little bit. So we're handling case Q2. Let's just think to ourselves how this could go wrong before we read what I have written here. So I have Q2 is on L2, P's over here. These 2 points are still on opposite sides of L1, and so what do I know?
That they have to have an intersection somewhere on L1.
That there has to be a point on L1 between P and Q, call R. So there has to be some point R on L1 between P and Q. Now how do I know that it's impossible for R to be down here? How do I know that R showing up down here is actually an impossible picture? So my segment can't come down and then go up like that. Because I can't use the same logic I used before.
Right.
Because PQ aren't on the same side of L2. Q is exactly on L2. It's not on the side of L2.
I mean, you can still say that if it does, then it intersects R2 twice.
So here's where we have to go with the intersects twice. Now, how am I going to know that intersects twice? I'm going to say, let's imagine R's down here, and that's going to break our picture. How is that going to break our picture? Well, because then R and P are on opposite sides of the line. And so there has to be some point between R and P on this line. Call it R2, or R prime, I think I call it. And so this segment, erase L for a second, this segment right here, how do I know that segment's impossible? It intersects L2 twice. Where does it intersect L2?
Q2 and R1.
Over at Q and over at R prime. And that's exactly what we're going to say. We're going to show that it's impossible for R to be down here, and so R has to be up here. And so R is in fact in the ray R1. Make sense?
Yeah.
Let's say that in words now. So next, if Q lies on one of the lines, say L2, then P and Q must be on opposite sides of L1, and so there exists R in L1 such that R is between P and Q. So R has to be somewhere on L1 between them. Now show it's impossible for R to be down there. If R is not on R1, we're going to get something impossible, and so R has to be on R1. If R is not on R1, if R is down here and not in this right R1, if R is down here, we're going to get this impossible picture. And therefore, R has to be in R1. I was going to do this proof by contradiction, but decided to just say it this way. But it's essentially proof by contradiction. So if R is not in R1, then R lies on the opposite side of L2 as P. So if R is not in R1, R is on the opposite side of this line as R1, and so R is on the opposite side of L2 as P. So there's a point between R and P on L2.
Yeah.
And so there must be some other point called R prime in L2, such that R prime is between R and P.
Right.
Got that?
Yes.
Okay, so now I have these two betweenness relations. So then I know that R is between Q and P, and I know that R prime is between R and P.
Yeah.
Which gives me that R prime is between Q and P.
Yep.
You see that?
Yes.
Here's R and P, and I know R prime's between them.
Yeah. So it has to be up here.
Okay, so I have Q, R prime, P. I know R prime's between Q and P. And if you have 3 points, if I have 1 point between 2 points, what do I know about all 3 of those points?
But they're in the line.
They all lie on the same line. They're collinear. And so these all lie on the same line. Q, R prime, and P all lie on the same line. And notice the problem with that line. So then QRP, oh sorry. So QRP and RR prime P gives us QR prime P, so R prime is between Q and P. And so the line through P and Q intersects L2 twice, which is impossible.
Right.
So R couldn't have been down here. And so our only other choice for R is up here. And so R had to have been in R1. And our segment looks like that, which is much more reasonable based on our intuition, right? Therefore, R is in R1, and so PQ intersects angle O.
Yes.
Good?
Yep.
Okay, now setting up the third case. So third case, oops, that's what we needed. Hopefully erasing all over this picture isn't making such a mess you can't see it. So now we've got P over here, and our third case is Q is on the opposite side of both lines. You with me?
Yep.
Now we're going to argue that PQ intersects this angle. How are we going to do it?
We know it's on opposite sides.
It's on opposite sides of both lines, so it's definitely on the opposite side of L1, for example, right? And so what does that mean?
There has to be a line that connects Q and P that intersects that one.
Yeah, there has to be a point on L1 between P and Q. We'll call that point R.
Okay.
Right?
Yep.
Now, either R could be somewhere down here, if Q was like that, or notice if Q were a higher point like this, then R would be somewhere like up here.
Right.
So 2 cases, R could be on R1, or it could be down here. Right?
Yeah.
If R is on R1, we're already done.
Right.
That means PQ intersects R1,
Yeah.
because there's a point on R1 between them. So now let's look at the case where R is down here.
Well, we know Q is on the opposite side of L2, so there has to be.
We don't even need to think that hard anymore. Case 2, we already know that if we have a point in the exterior on a line, and a point in the interior, that their segment intersects the angle. That was case 2. So I know that this segment intersects the angle. That's what we proved in the previous case. Therefore, this segment intersects the angle.
Recess.
Remember case Q2, this was Q3. Q2 was when we had a point right here.
Right.
A point on the line. And Q1 was up here. Here's our point P. So if Q3 is down here, then either the segment PQ, if Q is down here, it's Q3, then either the segment PQ intersects R1, or it intersects this line. And if it intersects this line at a point, I already know that this segment intersects the angle, because I already proved Q2 at this point intersect the angle,
Right.
where Q2 was any point on one of these lines. So we've already handled that part of the proof. You can reprove it all out if you want, but it's perfectly valid in your proof to use previous cases.
Right.
That's why we went through the cases that we went through, the order that we did. It's because maybe the easier case will help us in the harder case. Make sense? So that's what we're going to make reference to here. So starting over here. Finally, if Q is on the opposite side of both L1 and L2 as P, then there must exist R1 in L1 and R2 in L2, such that R1 is between P and Q, and R2 is between P and Q. So we'll ignore case Q1 and Q2 for a second. Here's our Q. So far we're saying, if Q's down here, P's up here, then there must exist 2 points, one on each of these lines, such that they're on opposite sides. So there must be some point R1 somewhere on here. R1's on L1, right?
Yes.
Yeah, R1's on L1. And R2 somewhere up here on this line, such that this point's between these two and this point's between these two. Now, if R2 is in the ray R2, we're already done. Because then Q, P intersects the angle. But R2 didn't have to be there. If I would lift this point Q drawn up here, then when it comes up, it would intersect, R2 would have been right here and R1 would have been up here. Okay, so if R2 is in the ray, little r2, we are missing Alexandria.
Oh my word! Where is he?
Her, Alexandria. We got Alexander.
What if I just call him Allie?
Works for me.
She goes by Alex.
She goes by Alex.
You could say Alex.
Oh, did I say Alex? That's what I put. Thank you. Okay, have a good day.
You
What?
too.
You guys are so smart. Look at that stuff.
All right. So, if R2 is in the ray, little r2, if we have this picture, then PQ intersects angle O, and we're done. We don't need to go any further.
Yeah.
On the other hand, our picture could have also looked like this. It could have been the case that our Q was higher up here. So if our Q were right there, then our R2 would have been right there, and then our R1 better be on here. Right? So assume R2 is not in this ray. So it's over here somewhere. And observe that R2 must be on L2. So assume R2 is not in the little ray, and observe that R2 must be on the line L2 still, and it's on the opposite side of L1 as P. R2 is on L2, and it's on the opposite side of L1 as P. Right? Notice how we started this case. If Q lies on the same side of one of the lines, call it L2, then P and Q must lie on opposite sides of L1. So this is exactly where our point Q2 was. R2 now lies exactly where Q2 did. And so we're just reproving case 2. Observe that we have already shown that segment R2P must intersect R1. This was lines 5 through 8 of our proof, where we handled that case.
Yeah.
Since R2P intersects R1, and since R2 is between P and Q, then PQ must also intersect R1.
Yep.
And so PQ intersects the angle O in either case.
Yep.
You follow that?
Yes.
Okay. Warning. 2 warnings. 1, the author does not give this full proof in the book. He only proves a piece of it and leaves proving the rest of the pieces of it to you as homework problems. So finishing off this proof will be homework for you. Now I did the full proof, so I did your homework. But I want you to be able to still reproduce it, make sure you understand this proof. It's a lot to absorb getting used to this. Good? And then our last definition of chapter 3 is the interior of a triangle. And you can almost guess it. So we know what the interior of an angle is. Now what's the interior of a triangle? So I've got some triangle. What's its interior going to be?
Yeah, all of the angles.
Yeah, look at this angle right here. And look at its interior. And intersect that with this angle's interior. And intersect that with this angle's interior.
Can't you just
It's the interior of all 3 angles that make up the triangle.
Can you do just 2 angles?
Yes, you can do it with just two angles, and that will be a homework problem for you. Is oh, you already did it?
Yeah.
Yeah.
3-1 to 3-6.
Oh, well, there you go. So yes, you could have just used two angles. Okay, so definition 311. The interior of a triangle is a set of all points interior to each of the triangle's three angles. The exterior of the triangle is a set of all points not on and not interior to the triangle. Make sense? Is this point on the triangle? No, it's in the exterior. Is this point on the triangle?
Yes.
Is it in the interior?
No.
No. Here's a point on the interior, there's a point on the triangle, there's a point in the exterior. Remember, just because you're in the exterior, just because you're not in the exterior does not mean you're in the interior, and vice versa. Because you could be on the actual triangle.
There's a problem that's like as you prove that a point that isn't in one of the angles but is in the other isn't in the interior of the whole triangle. If that makes sense.
Does make sense. So it's in the interior of one of these angles, but it's not in the interior of one of the other ones. So this point is in the interior of this angle, but it's not in the interior of this angle, so it's still in the exterior.
Yeah.
Yeah, that makes perfect sense. Okay, that ends chapter 3. Any more questions about chapter 3? That's a big chapter. Chapter 4, not as big. Let me move this chair.
Are there more exercise groups in chapter 4?
I would guess it's smaller. But I honestly have no idea. Have to just look at your syllabus. And even then, having more exercise groups doesn't say much because these exercise groups come in such various sizes.
Yeah.
Like we had one that was just one that we need to.
Yeah, they're pretty accomplished.
Oh yeah, I think I remember that 4-1. Both the questions are just like write this in your own words.
Yeah, there was a lot of that.
So 4-1 you can skip entirely. Exercise group 4-1.
We knew that before.
Yeah, 3-3 is one problem, and then 3-5 is two problems.
Yeah. So small stuff like that. If the problem ever says, do this in your own words, you never have to do those problems. I'm not sure if I said that this year.
I don't know. Did you?
I have no idea. I'm not going to go check the footage. Okay. So now we move on to our next chapter. Our next chapter, we just have one new undefined term. Congruence. This is our only new undefined term that we're introducing. Now again, these words are meant to capture some intuition we already have. So we're going to be talking about segments being congruent to each other. Intuitively, what does it mean for segments to be congruent to each other?
The same size.
They have the same length, the same size, right? Now, let's also think about this for a second. How would I know if two objects are different heights?
You can.
Compare them.
You compare them.
Yeah.
Well, we'll get to that when we talk about different lengths. Maybe I'll put that on hold for a second. So, say that in a second. So anyways, congruence, it means that two things are the same length, the same height, two segments are the same long. That's intuitively what it's meant to mean. Now let's think about just what our intuition and what we want to be true about congruence, if that's the notion we're trying to use congruence to capture. So our next postulate group only has 3 sets of postulates here, but each of the postulates has different parts. So, postulate group 3-1. What does it say? It says, given points A and B on a line L1, and a point A prime on L. So here's a B on a line L, and here's A prime on L prime. Ignore the back point so far. Here's your job. I give you A prime, and I give you this segment AB. I say, I want you, using this point, to construct a segment the same length as this. How would you do that? You could go to a point to the right and create a segment right there the same length, or you can go a point to the left and create a segment the same length there. There's 2 different ways you could do it, right? If you're going to use this point on your segment. That's one of the endpoints of your segment, right? And these are the only 2 points on this line that would make this resulting segment the same size as this. So if you go this way of A prime and use this segment, then this segment is the same big as that. Or you can go this way on A prime and use this segment, and then this segment is the same big as that. And intuitively, those are the only two ways you can do it. That's all this axiom is going to say, this postulate is going to say. So given points A, B on L, and a point A prime on L prime, there exist two unique points, two and only two unique points, call them B prime, on either side of A prime, such that AB, segment AB, this is congruent. It's an equal sign with a tilde on the top.
But it's not the same as equals, right?
It is not the same as equals.
What is the difference?
Let's pretend that you and I are the same height. Then you are congruent to me. Are we the same person?
No.
Equals means identity, means the same.
Yeah.
So let's say that AB is congruent to A prime B prime. Is this segment equal to this segment?
No.
No. The only way that this segment is equal to this segment is if they're identical segments. They are the same segments. They're the exact same set of points. That is a different point than that. So they can't be the same.
Right. That makes sense.
Okay. So far got good intuition for congruence?
So congruence, like, is just the symbol for it is just an equal sign for the.
With the little squiggle on the top, a little tilde on the top. Correct.
Okay.
Okay. Axiom 2 is that congruence is an equivalence relation. For those of you who have taken more classes with me. For those of you that haven't, don't worry. That just means it has three properties. Number 1, every segment is congruent with itself.
Yep.
Am I the same height as me?
Yes.
Are you the same height as you? Will always be the case that everyone's the same height as themselves.
Yes.
That's all this is saying. Every segment is the same long as itself. We call this a reflexive property. Every segment is congruent to itself. Good? Now, if I'm the same height as John, is John the same height as me?
Yes.
Yes.
That's what this one says. If AB is congruent to A prime B prime, then A prime B prime is congruent to AB. We call that property, you remember? Those of you who've done classes with me?
Communicate.
No, commutative. I see how it's kind of similar to that, but commutative has to do with operations. Notice that this is a relation. You give it two segments and it spits out true or false.
Reflective.
This is a reflexive property. This is a symmetric property.
Right. Yes.
If this is true, then its mirror image is true. Okay, and then finally we have the transitive property. If I'm the same tall as John, and John's the same tall as Jack, am I the same tall as Jack?
Yeah.
Yes, and that's a commutative property. If AB is congruent to CD, and CD is congruent to EF, then AB is congruent to EF. Make sense?
Yep.
Okay. So these are special properties that equivalence relations all have. Congruence is a particular equivalence relation. Not all relations have these properties.
One example that doesn't.
Let's pick another relation. Let's pick the less than relation. Is it true that everything is less than itself?
No.
No.
Oh.
Is it true that if x is less than y, y is less than x?
No.
No. Is it true that if x is less than y and y is less than z, that x is less than z?
Yes.
Yes. So less than is transitive. It has this property,
But that's it.
but it didn't have these two. What if we did less than or equals? Is everything less than or equal than itself?
Yes.
Yes. Is it true that if x is less than or equal to y, that y is less than or equal to x? No. Is it true that if x is less than or equal to y, and y is less than or equal to z, that x is less than or equal to z? Yes. So less than or equal has this property, not this property, has this property. So some relations out there happen to have all three properties. Those relations we call congruence relations. They're the relations that are saying two things are somehow the same.
Equivalence relation.
What did I say?
Congruence relation.
I am going to do that so much. Don't let me do that. Equivalence relation, yes.
I was a little confused.
Thank you. Any relation that has these three properties is called an equivalence relation. Equivalence relations are always saying two things are somehow the same. Those of you who go all the way back to topology, what was the sameness relation that we used?
It was a
Homeomorphisms. Are two things homeomorphic to each other? A homeomorphism was a congruence relation,
equivalence.
an equivalence relation. Blah.
Yeah. You proved that, right?
Yes, you show it has these properties. Another common one is set cardinality. How many elements are in a set? That has this property. Does every set have the same number of elements as itself?
Yes.
Yes. If set A has the same number of elements as set B, does set B have the same number of elements as set A? Yes. And if set A has the same number of elements as set B, and set B has the same number of elements as set C, does set A have the same number of elements as set C? Yes. And so we called two sets that had the same cardinality isomorphic. They're somehow the same. Two topologies that were somehow the same we called homeomorphic. Two geometric figures that are somehow the same we call congruent. So congruence is the sameness relation that we care about in this class. Typically, pick a field and there's some sort of relation in the field that captures sameness that the field cares about.
Why do they change it in different?
They mean different things. Saying two geometric figures are congruent is not saying the same thing as two sets have the same size.
Yeah.
Those are two different things. Notice that just because you can think about these as sets of points, right? Some geometric figure as a set of points. And if these two segments somehow had the same number of points, the same cardinality, that doesn't necessarily mean that they're congruent. So those sets might be isomorphic to each other, in the sense that their size is both the same infinity. On the other hand, those figures are not congruent to each other. So the sameness relation you care about depends upon the field you're in. We're in the field geometry. The sameness relation that we care about, the equivalence relation that we care about, is congruence. So these three properties show up in pretty much every field of mathematics. There's relations that you're dealing with that have all three of those. In this class, it's going to be congruence. Okay, said a lot about that. Finally, our last postulate for this chapter. It's often phrased as the mnemonic you use is equals added to equals are equal, and equals subtracted from equals are equal. That's the way it's often phrased. I'll give it to you exactly, and I'll make the mnemonic make sense. So, if B is between A and C on line L, and B prime is between A prime and C prime on line L prime, then if we have AB congruent to A prime B prime, if AB is congruent to A prime B prime, and BC is congruent to B prime C prime, BC is congruent to B prime C prime, so I know this length is the same as this length, and I know this length is the same as this length, then what do I know? Follow me here. I know this red length is the same as this red length, and I know this blue length is the same as this blue length. What do I know? That this total length is the same as this total length.
Yeah.
So I start out with two equal pieces, and I add an equal amount to both of them, and the result is equal. Equals add to equals are equals is the mnemonic that you use to help you remember this.
Makes sense.
So if that is congruent to that, and this is congruent to this, then this whole thing is congruent to this whole thing. So it's a way of adding segments together is what this gives us. And then this one gives us a way of subtracting segments from each other. So what's this one going to say? It's going to say, if red's the same size as red, and this whole thing is the same size as this whole thing, then this piece has to be the same big as this piece. In other words, if my starting size is the same with both of them, and I cut off the red piece from both of them, and the amount I cut off is the same, my result is the same. So if I start with two equal pieces, and I subtract off an equal amount from both pieces, my result is equal. Equals subtracted from equals are equals is the mnemonic people use to remember it. Let's read it precisely now. If AB is congruent to A prime B prime, and AC is congruent to A prime C prime, then BC is congruent to B prime C prime. You got it? Okay. Now technically, we don't need to introduce this one as an axiom. It could have been proven from what we gave you up here.
Really?
Yes. For your homework, you are allowed to use it as an axiom, But I think that there's going to come up a homework problem or an extra credit problem that says try to prove this from these postulates.
Why is it an axiom if you can prove it?
For the sake of the reader's convenience. For the sake of the student. So it doesn't have to be an axiom. It doesn't really add anything giving us that axiom. But we're going to give it to you for the sake of helping you do your homework.
Okay.
Make it easier to use. Okay, that makes sense? Okay, with that, let's jump into our first theorem here. Just got 4 theorems and then we're done. One definition first. Let AB be a segment. Okay, so now here's where I'm going to talk about different size things. Because here's where we're going to talk about one segment being longer or shorter than another. How would I know if Jack is taller than me? How would we figure this out?
If when you line yourself up with him, he's up here to be taller than you.
So-
If you measure both of you, and then you compare.
So one way to do it is to actually measure us and then look at those two numbers. That's one way to do it, introducing numbers into the system. But you don't really need to, it's using more than we need because a measurement still requires some sort of metric. What does it mean to say that I am 5 feet tall and however many inches?
It means that you have a metric of feet that you can measure yourself by.
Yeah, like, it's just.
It requires an understanding of what 5 feet is.
It requires an understanding of what a foot is. What's a foot?
12 inches.
Okay, what's an inch? You're not answering my... Imagine that we brought some complete foreigner in here who's never heard of any of this stuff. You're trying to tell him that you're 5'6". He says, what does that mean? What's a foot?
It's how long light travels at a certain amount of time.
Eventually, somewhere out there, while we have this for a meter, there is some platinum rod over in France somewhere, and its length is what we mean by a meter. What is a meter? It's how long that rod is. Right?
Yeah.
And so if we lived in some tribal village out before any of this stuff existed, and we wanted to compare heights, there's 2 ways that we could figure out. So I'm in my tribe, I want to know, is my son taller than your son? One thing I might do is I might go get a stick, cut it off as tall as my son is, and then walk over to your tribe and have your son go stand next to it. Right? And how would that actually go? Let's think about that physical process. So I get the stick. Here's the stick that I have representing my son's height. And I have your son come stand up next to it. And your son, he's right here, and he goes up like this and then cuts off right there. Who's taller? Red or blue?
Red.
How do you know?
Because there's more points in red.
Because when we mark this over and we create a blue point here, so that this is the same long as this, the point that we added is between these 2 points.
Oh, yeah.
Notice that another way we could have done this is it could have been red was like this, and blue was like this, right? Maybe your son was taller. Now when we come over and we mark the point so that this segment is congruent to this segment, notice now the point that we added is beyond those 2 points. So we're going to call this a point A, B. We're going to call these points over here A prime, B prime. And we're going to be adding a point B double prime. And B double prime can either show up here or it can show up above. So these are our 2 possible pictures. A, B, here's B double prime. Here's A prime, here's B prime. So my son is A prime to B prime, your son is A to B. If when we take your son's height and we mark it over to the point B double prime, if it comes between these 2 points, my son must have been taller. If it comes beyond those 2 points, your son must have been taller. So we're defining this greater than relation. That's what we're about to define. Remember that we have to define this only using words in our vocabulary.
Right.
And what are the words we have in our vocabulary?
Feet and inches.
Between
No. In our geometry vocabulary.
congruence, betweenness.
We have line, point, plane, congruence, between, and those are the only relations. The only relations we have defined so far are congruence and between.
Right.
if I'm defining some new relation, I have to define it using the words congruence and between. And notice that's what we said here. We said pick the point B prime so that this is congruent to that, and then check if B double prime, pick the point B double prime so that this is congruent to that, and check if it's between. Mark the point B double prime so that this is congruent to that, and check if B prime is between. So we're only going to use congruence and between to define less than or greater than. We can only use words already in our vocabulary. So now let's read the definition exactly. And this is the hard definition of this chapter. Just like being in the interior of the angle was a hard definition in chapter 3, this is the hard definition in chapter 4. So let AB be a segment, and let A prime B prime be a different segment on L prime. With me so far? A prime B prime, that's going to be my sun type. AB is going to be your sun type. Let B double prime be the point on the same side of A prime as B prime. So whatever B double prime is, it has to be on this side of A prime. So pick B double prime so it's on the same side of A prime as B prime. Notice in both these pictures it is. So let me say it again. Let B double prime be the point on the same side of A prime as B prime, such that AB is congruent to A prime B double prime. If B prime was between A prime and B double prime, then AB must have been taller than A prime B prime. That's this picture. If B prime was between A prime and B double prime, AB was greater than A prime B prime. If the B prime was between the A prime and the B double prime, that meant AB was bigger. And if the B double prime, the top picture, if the B double prime was between A prime and B prime, then that meant AB was smaller than A prime B prime. That makes sense? And so here's also the picture. Here's the picture for AB is bigger than A prime B prime. Your B double prime is over here. Here's a picture for AB is less than A prime B prime. Your B double prime is between A prime and B prime. Make sense?
Yes.
Okay. It is going to be very tempting to go from saying AB is greater than A prime B prime to saying that A prime B prime is less than AB. You have to be very careful. This and this say different things. And you are going to likely confuse the two. It turns out that this and this are logically equivalent, and we'll prove that. But they do not say the same thing. They give us different betweenness relations.
Logically equivalent between these relations.
It turns out that they're logically equivalent, but that's not trivial. It's intuitive, but it's not trivial. So we'll do that proof, but just want that warning because you're likely going to make that mistake. Okay, let's prove our first theorem. Given any two segments, AB and A prime B prime, then we have one of three cases. Either AB is greater than A prime B prime, AB is congruent to A prime B prime, or AB is less than A prime B prime. Has to be one of those three cases. Good? So far? Understand what we're trying to prove?
Yes.
Let's prove it. So let AB and A prime B prime be segments. Let L2 be the line through A prime B prime. And let B double prime be on the same side of A prime as B prime, such that AB is congruent to A prime B double prime. So what are the three possible cases we could have? Here's my AB. Just a segment. And now we've got some line down here. We'll draw a line for each of the three cases. I can have it so that A prime and B prime look like this. A prime, B prime smaller than AB, right? So now if I come down and I mark a point on this line, call it B double prime, so that A prime, B double prime is the same length as AB, then we're going to get B primes in the middle.
Yes.
It could have also been the case that we had something like this. A prime, B prime, and B double prime happen to land right on B prime.
Yeah.
In that case, the segments are going to be congruent. The third case would have been something like this. We had A prime, we had B prime, and B double prime lands between them. So it's going to have to be one of these three cases.
And it can't be before
We're going to pick B double prime to be on the same side of A prime as B prime. So B prime and B double prime have to be on the same side of A prime. The only question is which one comes first.
A. Okay.
It could be B prime comes first, it could be actually they're tied, or it could be B double prime comes first. So I've got A prime, here's AB, here's my segment AB. A prime, B prime could be a smaller segment, it could be a same size segment, or it could be a bigger segment.
But do we have to like say, like define that it has to be on the same side as A1?
Well, we're going to choose that point. So let AB and A prime, B prime be segments. So we start with any two segments. We have AB, and then either this segment, this segment, or sorry, yeah, this segment, ignore the B double prime so far, this segment, or this segment. So let those be any two segments. Let AB and A prime, B prime be segments, and let L2 be the line through A prime, B prime. So I'm just going to put a line through the A prime, B prime segment, just so I can talk about another point on the line. And let B double prime be on the same side of A prime as B prime, such that AB is congruent to A prime, B double prime. So B double prime is always going to be the point that makes the segments congruent. You with me?
Yeah.
So we've got the three cases. Either B prime happens to be the same point as B double prime, or they're not the same point. Has to be one of those two cases, right? If B double prime is the same point as B prime, if they're equal, they're actually identical, they're actually the exact same point, that's what equals means. So if the points are identical, then AB is congruent to A prime, B prime. Because AB is congruent to A prime, B double prime, but B double prime is the same thing as B prime. This says the same thing as this if they're equal.
Yes.
How do I know that?
Because your identity, your law.
From identity, law of identity, substitution. Equals may be substituted for equals. If those two are equal, replace B double prime with B prime. This says the exact same thing as that.
Yes.
Good? Okay, so we handled the case where the points are same. If the points are not the same, then since B prime and B double prime are on the same side of A prime, we either have B prime is between A prime and B double prime, or B double prime is between A prime and B prime. Has to be this between this relation or this between this relation.
Yeah.
A can't come between them.
Because that's the way you define it. Right?
Well, there are 3 points on a line, and you have one of 3 equivalence relations, or one of 3 betweenness relations. Either B prime's in the middle, B double prime's in the middle, or A prime's in the middle. But I know A prime can't be in the middle, because B prime and B double prime are on the same side of A.
Right. Right.
So A can't be in the middle of them. So we know we have this betweenness relation or this betweenness relation. If we have that B prime is between A prime and B double prime, then that's the exact definition of AB is greater than A prime B prime. What does it mean for AB to be greater than A prime B prime? Just write that as a side note here. This thing is logically equivalent to saying that AB is congruent to AB double prime, and we have A prime B, oh sorry, there's a prime there, B prime B double prime. That's what AB greater than A prime B prime means. It means these 2 pieces of information. We already have this piece of information right there. And now we're saying if A prime B prime B double prime, then that gives us this. AB is greater than A prime B prime. This definition is going to be hard for you to take in. It's going to take a couple times. What does it mean for AB to be greater than A prime B prime? It means that when you choose this point B double prime, such that A prime B double prime is congruent to AB, B double prime goes beyond B prime. Right? And similarly, if we have A prime B double prime B prime, then we have AB is less than A prime B prime. What is this logically equivalent to? When I say that AB is less than A prime B prime, that means that AB is congruent to A prime B double prime. And then this time, we have A prime
B double prime.
B double prime B prime.
You used a prime on your first
Yeah.
equalizer.
In after Congruence.
Because I put 2 on B. Oh, no. You're right. I just missed that. Thank you. Probably should have used instead of primes C's and D's. Probably hard to see those primes from so far away. Let me write that a little bit cleaner. That means AB is congruent to A prime B double prime, and we have A prime B double prime B prime. So that is what this means. What does it mean for AB to be less than A prime B prime? That means that when you pick B double prime such that AB is congruent to A prime B double prime was between A prime and B prime. Right? That's this picture right here. The B double prime comes between A prime and B prime. That is when AB is less than A prime B prime. Make sense? Okay. So there we go. Definition 4.2, you could have almost guessed this without me telling you it. Here's the definition. What does it mean for AB to be greater than or equal to A prime B prime? It means that AB is greater than A prime B prime, or AB is congruent to A prime B prime. Similar for what does it mean for AB to be less than or equal to A prime B prime? It means that AB is less than A prime B prime, or AB is congruent to A prime B prime. Make sense?
Yes.
Shorthand notation. Okay. 2 more proofs. Here's the one that you're going to want to use all the time. I'm only proving one direction of this. The other direction is going to be a homework problem. It's going to be a hard homework problem. So we are proving that AB is greater than A prime B prime, is logically equivalent to A prime B prime is less than AB. I'm going to prove this direction. I'm going to show that if this is true, then this is true. On your homework, you're going to have to show that if this is true, then this is true. Okay? Let's jump in. So I'm going to show this direction. So I'm going to show this implies this. I'm going to show if this is true, then this is true. How do you prove an if-then statement?
You assume the antecedent shall not apply to the conclusion.
Assume the antecedent, show that applies to conclusion. So I'm going to start out with let A be on L and A prime B prime on L prime such that AB is greater than A prime B prime. Right? Assume the antecedent. So I've got AB here and A prime B prime here.
Okay.
You with me? Now, kind of ignore C and D for a second here. Here's our picture so far. I know that AB is greater than A prime B prime. Right?
Yes.
So I know that if we mark this point B double prime down here, so that A prime B double prime is congruent to AB, then it falls beyond B prime.
Yes.
Right?
Yes.
What am I trying to prove? I'm trying to prove that A prime B prime is less than AB. I'm trying to show that A prime B prime is less than AB. How do I show this is true? I need to find some point that A prime B prime is congruent to. I need A prime B prime is congruent to, I'm going to choose a point AC. And I need to show that it goes A, C, B. So I need to prove that there is some point C over here that satisfies these two things. And if we can, we're done. You with me?
Yes. That makes sense.
Okay, so here's our picture so far. Well, kind of. We didn't do the B double prime yet. So here's our picture so far. Let AB be greater than A prime B prime. That's all we have so far, right? So since AB is greater than A prime B prime, what does that mean? Then there exists some point B double prime in L prime, some point in this line, such that AB is congruent to A prime B double prime, and B double prime goes beyond B prime. So that is what guarantees me now that there's this point. With me so far?
Yeah.
Okay. Now I'm going to pick the point C on this line such that AC is congruent to A prime B prime. So then how do I know that there exists a point C on this line such that AC is congruent to A prime B prime? How do I know that point exists?
One of your,
Our very first postulate. If you're given any segment and a point on a line, there exists some other segment congruent to that segment on a particular side, whichever side you want.
exactly.
So there is a point C on the same side of this line as B, such that AC is congruent to A prime B prime. So then there exists C in line L on the same side of A as B, such that AC is congruent to A prime B prime. I know this from postulate 3.1.
Okay.
Now, I do not know if C is right there or if C is somehow over here. I can't just assume that C is between A and B. Maybe the C somehow ends up over here. I need to show that the C ending up over here is an impossible picture. So it remains to show that C is between A and B. The way I'm going to show that C is between A and B is I'm going to show that it's impossible for C not to be between A and B.
Why do you say that little line there remains to be shown the ACD?
To make it clear to the reader, that's just to help the reader. To let the reader know that here's all that we need to do in the rest of the proof.
Is that a,
It's just to call attention to the reader so that they don't get lost in the proof and forget what it is we're trying to do.
okay.
So all we're trying to do now is show that C is between A and B, and we're done. If C is between A and B, if we can show that this is our picture, we're done. But we don't know that that's our picture. Because C could have been over here, or C could have been the point B. And we need to show that both those are impossible. So let's first look at the case where C and B are the same point. So that is a point B and C. Let's show that that's impossible. If C equals B, then I know that AB is congruent to AC. How do I know AB is congruent to AC?
Because B and C are the same.
Because B and C are the same point, and that comes from the reflexive property.
Yes.
Every segment is identical with itself. If C and B are the same point, then AB is AC. And so AB is congruent to AC. Because every segment are congruent with itself. And I know that AC is congruent to A prime B prime. How do I know that?
Because AB was congruent, or because by
AB.
definition AC is congruent.
We chose C such that AC is congruent to A prime B prime. We're going to be referencing this a lot, so maybe put a box around it. How do I know this piece? That's how we chose a point C. We found the point C on this segment that made this true. Contradicting the fact that AB is greater than A prime B prime. Here I have AB is congruent to A prime B prime, kind of skipping a step. I know AB is congruent to AC is congruent to A prime B prime. How do I know that AB is congruent to A prime B prime?
Because of your postulate.
The transitive property.
Yep.
So, using the transitive property behind the scenes. Should have been more explicit. Make sense so far?
Yes.
So I know that AB is congruent to A prime B prime, contradicting the fact that AB is greater than A prime B prime. How is that a contradiction?
Because it's not greater than or equal to.
Because of what we just proved over here. That you can only have one of those three cases be true. Either one segment's less than another segment, or the two segments are congruent, or one's greater than the other segment. Has to be one of those three cases. I cannot have AB is the same length as A prime B prime, and AB is greater than A prime B prime. AB is greater than A prime B prime is what we started with.
Right.
That's how we set up our picture. We set up our picture so that AB is greater than A prime B prime. So we can't have AB is congruent to A prime B prime. Contradiction. So I know it's impossible for B and C to actually be the same point. So next I'm going to show that it's impossible for C to be over here. It's impossible for it to be over here and B to be between A and C. That's the next thing I'm going to show is impossible, and therefore C had to have been right there. You with me?
Yes.
Okay. So here we've handled the case where C is equal to B, so that's impossible. Now if B is between A and C, we got to show that this is impossible. Okay. So if B is between A and C, then there is some point D in L, such that D is beyond C, C is between A and D, and CD is congruent to B prime B double prime. So if C is over here, I can pick this point D, such that this segment is the same long as this segment. You with me?
Yeah.
Now, if AC is the same big as A prime B prime, and CD is the same big as B prime B double prime, how does this length compare to this length?
It should be congruent.
Remember, we got a line picture here.
Right.
So far in our picture, what have we said? We said that AC is congruent to A prime, B prime. So this piece is the same big as this piece.
Yeah.
And this piece is the same big as this piece.
So the total should be congruent.
So this total is the same big as this total.
Yeah.
That's using this axiom,
Yes.
right?
Yes.
And then if this total is the same big as this total, I already know this total is the same big as this total. So I get this is the same big as this, but this is the same big as this. So this is the same big as this.
Which is absurd.
Which makes B and D the same point. Which doesn't work. Because B is between A and D.
That's it.
So that's going to be impossible.
Oof. Okay.
It's a bit of a lot to take in, so I will explain it and then we go through the words and explain it again. So, if C is a point such that B is between A and C, then there exists D and L such that C is between A and D, C is between A and D, and CD is congruent to B prime, B double prime. This segment CD is congruent to this segment B prime, B double prime. So then AC is congruent to A prime, B prime. How do I know that? Right here. Told you we use this box a lot.
Yep.
AC is congruent to A prime, B prime. And CD is congruent to B prime, B double prime. Gives us that AD is congruent to A prime, B double prime. By Postulate Group 3, Axiom 3. By 3 over there. So then I have AB is congruent to A prime, B double prime. And I have A prime, B double prime is congruent to AD. So that gives me that AB is congruent to AD. Using the transitive property. So by postulate 3-2. Using this. And then by 3-1, this gives us that B is equal to D. How do I know that this gives us B is equal to D? If AB is congruent to AD, how do I know that saying B and D are the same point? Because there's only one point on this side of A with that length. That was our first postulate here. Given some segment here, there's only one point on this side B prime, such that this segment is congruent to this segment. I now have 2 points on this side of A, both B and D, such that this segment is congruent to this segment, and this segment is congruent to this segment. So B and D have to be the same point, which is impossible. How do I know it's impossible? Because B is between A and D.
Right.
And going all the way back to our betweenness relations, if you have 3 points, 1 point between 2 other points, all 3 of those points are distinct points all in a line.
Yes.
So B and D can't be the same point, which is impossible. So therefore, the C is, as we expected, the C has to show up between A and B. So therefore, we get C is between A and B, and so A prime, B prime is less than AB. That's the hard proof of this chapter.
And we have to prove the other side of that.
And you're going to prove the converse. You're going to show that if this is true, then this is true.
Wow.
I only showed if this is true, then this is true.
That's not the worst thing.
No, it's not the worst thing. It's kind of doing the picture, but you're going to be doing a bunch of work down here. Or you're going to start with points up here and then put the lines. I'm not going to try to say it in a high level way. It'll sound bad. Just read carefully exactly what your definition gives you. Okay. Next one. Theorem 4.3. If AC is congruent to A prime C prime, and B prime is between A prime and C prime, and B is on C prime's, on C's, probably shouldn't do apostrophes like that. I'm going to get rid of the apostrophe even though it is ownership just because I don't want to think we're talking about C prime. Okay. And B is on C's side of A, such that AB is congruent to A prime, B prime, then B is between A and C. What is this saying? So that's this picture. So AC is congruent to A prime, C prime. And B prime is a point between A prime and C prime. We're saying, come mark the point up here. Mark the point up here, B, so that AB is congruent to A prime, B prime. And B is on the same side of A as C. Then B has to be between A and C. It couldn't have ended up over here. Make sense?
Yeah.
Say it again. If AC is congruent to A prime C prime, and B prime is between A prime and C prime, and B is a point on C side of A, so B is a point somewhere over here.
Yeah.
Where over here? It's the point over here, such that AB is congruent to A prime B prime.
Oh.
So B is a point over here, such that AB is congruent to A prime B prime. And the only question remains, is B between A and C, or does it somehow get beyond C?
Right.
And obviously, it has to be between A and C, and that's what we're going to prove. So then B is between A and C. So we're proving this is the right picture, B over here is the wrong picture. Make sense? Okay. Pretty straightforward proof using what we did up here. So first off, let AC be congruent to A prime C prime, just so I get my picture here. Let B prime be between A prime and C prime, and let B be on C side of A, such that AB is congruent to A prime B prime. Setting up this picture. Good? Since AC is congruent to A prime C prime, and since B prime is between A prime and C prime, then I know that AC is greater than A prime B prime. What does it mean to say that AC is greater than A prime B prime? It means that when you draw the point that makes, when you draw the point congruent to AC, that B prime came between them. How do I know AC is bigger than A prime B prime?
When you draw the points.
When you have C prime here, B prime is between them.
Okay.
That's what it means.
Yes.
So since I have that, I have AC is greater than A prime B prime. My picture gives me that for sure. I can get that from just the blue points. Don't need the red point. Remember, we're trying to figure out where the red point is. Now, from our theorem up here, if AC is greater than A prime B prime, what do I know? Using this theorem, if I know that AC is greater than A prime B prime, what do I know?
Then A prime B prime is greater.
Then A prime B prime is less than C prime. And what does it mean for A prime B prime to be less than C prime? It means that if we come mark a point B up here, so that A prime B prime is congruent to AB, B has to be between A and C. That's what it means. So then A prime B prime is less than AC, and since A prime B prime is congruent to AB, then B has to be between A and C. And so it's just as simple as flipping the inequality when you understand what these inequalities mean. It's really hard to understand what these inequalities mean. One more small theorem, then we're done for the day. Theorem 4.4. If AB is greater than CD, and CD is congruent to EF, then AB is greater than EF. These were all meant to be points on a line. I didn't set up the theorem all the way. I kind of summarized it. But here's our picture. So if AB is greater than CD, so I have AB, CD. So I have AB is greater than CD, and CD is congruent to EF. This isn't the one I thought I was proving. Sorry. AB is greater than CD, and CD is congruent to EF. How does AB compare with EF?
It's great. It's great.
AB is greater than CD, CD is congruent to EF, therefore AB is greater than EF.
Yes.
That's what we're proving.
Makes sense.
Okay, so let AB be greater than CD, and let CD be congruent to EF. Good? And observe that since AB is greater than CD, that means that CD is less than AB.
Yes.
That's using this one. So if CD is less than AB, what does that mean? Now see why I called my point. I call it B prime. Okay, since CD is less than AB, then that means that we can find some point up here. Let me draw my AB the way that it's going to make better sense with our picture. Here's AB. Okay, Since AB is greater than CD, that means that there exists some point up here called B prime, such that B prime is between A and B, and AB prime is congruent to CD.
Yep.
So, then there must exist B prime, such that CD is congruent to A prime B prime, and B prime is between A and B.
Yep.
You with me?
Yes.
Okay. Now, I know that EF is congruent to what?
CD.
CD, but CD is congruent to what?
A prime.
And
AB prime. So EF is congruent to AB prime. So EF is congruent to AB prime, and B prime is between A and B. That's exactly what it means for EF to be less than AB. So, since EF is congruent to CD is congruent to A prime B prime, then EF is congruent to A B prime. And B prime is between A and B double prime. Sorry. EF is congruent to A B prime, and B prime is between A and B. With me? Okay. Therefore, EF is less than A B prime. What does it mean for EF to be less than? My goodness. You can tell this was my last theorem. So many mistakes. EF is congruent to AB prime. B prime is between A and B. That's exactly what it means for EF to be less than AB. Okay. So, that gives us that EF is less than AB, which is the same thing as AB is greater than EF. Okay, there we go. So we show that if AB is greater than CD and CD is congruent to EF, then AB is greater than EF. Make sense? So I flip my inequality so I can work with points on this line rather than points on these lines. And then flip the inequality back. That's it for chapter 4. A lot to take in. Finishing up chapter 3, a lot of chapter 4.
That's all chapter 4.
That's all chapter 4. 2 hard definitions. Well, for chapter 4, it's just one hard definition. This definition of being greater than or less than. It's very hard to keep in mind what exactly that gives you. The exact picture that gives you. And it's the picture I tried to draw for you there, or the picture I have drawn for you here.
Yeah.
You're going to want to go backwards and put the points up here. Or you just want to say it's obvious. And you're going to feel like, how do you even say this? Obviously, if A is less than B, then B is greater than A. A duh. Nope, there's no a duh. You have to go back and think about it in terms of the congruences it gives you and the betweenness relations it gives you. Remember that this is using congruence and betweenness. So think about what exact congruences it's telling you and what exact betweennesses it's telling you. Okay, any questions?
How many more postulate groups do we have?
Not a clue. We've already covered probably half the postulates for the class, I would guess. Go ahead.
Why are we doing like primes instead of subsets?
Instead of
Like the thing at the bottom.
subscripts.
Subscripts, sorry.
So there is no special reason to use primes rather than subscripts, rather than different letters. I'm trying to be consistent with your author so that you're seeing the same notation both for me and him. That's the only reason.
Okay.
So nothing special about the primes, it's just what he uses. I don't really like using the primes very much because
Apostrophe.
apostrophes is one of them, and then
And then
Yeah.
calculus is another reason.
Oh, yeah.
But trying to follow what the author does, trying to give you the same definition with the same pictures that he'll give you. Anything else? Cool. All right, we'll do break and then come back and we'll check homework.